The geocentric universe. Ancient astronomers observed the sun, moon, and stars, and 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. The sun, moon, and stars all have simple movements in the sky. The planets move with respect to fixed stars, change in brightness, change speed, and they undergo retrograde motion. Inferior planets are Mercury and Venus, and the superior planets are Mars, Jupiter, and Saturn. We now know that inferior planets have orbits closer to the Sun than the Earth, and superior planets' orbits are farther away. The geocentric universe early observations. Inferior planets were never too far from the Sun, and superior planets are not tied to the Sun, and they exhibit retrograde motion. Superior planets also have brightness at opposition, and inferior planets have brightness near inferior conjunction. The geocentric universe earliest models had Earth at the center of the solar system. The geocentric universe needed lots of complications to accurately track planetary motions. The heliocentric model of the solar system is where the Sun is at the center of the solar system. Only the Moon orbits around Earth. Planets orbit around the Sun. This figure shows retrograde motion of Mars. The foundations of the Copernican revolution. Earth is not at the center of everything. The center of Earth is the center of Moon's orbit. All planets revolve around the Sun. The stars are very much farther away than the Sun. The apparent movement of the stars around the Earth is due to the Earth's rotation. The apparent movement of the Sun around the Earth is due to the Earth's rotation. Retrograde motion of planets is due to the Earth's motion around the Sun. The birth of modern astronomy. The telescope was invented around 1600. Galileo built his own and made observations. The Moon has mountains and valleys. The Sun has sunspots and rotates. Jupiter has moons, and Venus has phases. Phases of Venus cannot be explained by the geocentric model. The laws of planetary motion. Kepler's laws were derived using observations made by Tycho Brahe. Planetary orbits are seen as ellipses, the Sun at one focus, major axis and semi-major axis at the others. The imaginary line connecting the Sun and planet sweeps out equal areas in equal time. Square of a period of planet's orbital motion is proportional to cube of semi-major axis. The semi-major axis and eccentricity of orbit completely describe it. Perihelion, which is the closest approach to the Sun, and aphelion, which is the farthest distance from the Sun. The dimensions of the solar system. An astronomical unit is the mean distance from the Earth to the Sun. It was first measured during transits of Mercury and Venus using triangulation. The dimensions of the solar system are now measured using radar. The ratio of mean radius of Venus's orbit to that of Earth is very well known. Newton's laws of motion explain how objects interact with the world and with each other. Newton's first law: an object at rest will remain at rest, and an object moving in a straight line at constant speed will not change its motion unless an external force acts on it. Newton's second law: when a force is exerted on an object, its acceleration is inversely proportional to its mass. A equals F divided by M. Newton's third law: when object A exerts a force on object B exerts an equal and opposite force on object A. Gravity. On the Earth's surface, acceleration of gravity is approximately constant and directed toward the center of the Earth. For two massive objects, gravitational force is proportional to the product of their masses divided by the square of the distance between them. Gravity. F equals G times m of 1 times m of 2 divided by r squared. The constant G is called the gravitational constant. It is measured experimentally and found to be G equals 6.67 times 10 to the negative 11th n m squared divided by kilograms squared. Kepler's laws are a consequence of Newton's laws. First law needs to be modified. The orbit of a planet around the Sun is an ellipse, with the center of mass of the planet, Sun system, at one focus. Newtonian mechanics tells us that the force keeping the planets in orbit around the Sun is the gravitational force due to the masses of the planet and Sun. This allows us to calculate the mass of the Sun, knowing the orbit of the Earth. M equals RV squared divided by G. The result is M is equal to 2.0 times 10 to the 30th kilogram. Escape speed. The speed necessary for a projectile to completely escape a planet's gravitational field. With the lesser speed, the projectile either returns to the planet or stays in orbit. First models of solar system were geocentric, but couldn't easily explain retrograde motion. Heliocentric model does. Also explains the brightness and variations. Galileo's observations supported heliocentric models. Kepler found 3 empirical laws of planetary motion from those observations. Laws of Newtonian mechanics explain Kepler's observations. Gravitational force between two masses is proportional to the product of the masses, divided by the square of the distance between them.